with that, we can start on to what we finished last Wednesday, which was on branch pipes. So let's bring this up. Why isn't that coming up here? You guys see that okay? Or do you want the other light off too? You don't care? So that or that? The first one?
Oh, I get over
there. That one there? Okay. All right, so branch pipes. So the question that we want to ask ourselves now, what happens when the branch, when the pipes branch or converge? So they branch over here and converge over here. So converge or diverge, all right? So we can ask ourselves, what do we know about this given situation? I've labeled the pipes A, B, C, and D, and I'm going to go ahead and label these connections right here as nodes, 1 and 2, all right? So the concept of converge or diverge occurs at a node. Excuse me. Thank you. A node, or we're also going to call this a junction. Okay, those are used interchangeably. So when we look at this, just given the basic fluids background, what can we say about this right here? All right. Specifically, what can we say about the flow at A compared to what's going on at A and B? So let me say that again. We're looking at this pipe network. Flows coming in at A, splitting around B and C, coming back together at junction 2, and going out through D. So what can I say about node 1, relative to the conservation of mass? What can I say? What is the relationship between Q sub A, Q sub B, and Q sub C?
Q sub A equals Q sub B plus Q sub C.
Yeah. Q sub A equals Q sub B plus Q sub C. Right? Pretty fundamental of what we have coming in from pipe A is going to split and go through B and C, and it has to, because there's nowhere else for it to go. And the corollary at node 2 is the same thing, right? That Q sub B and C equals Q sub D. Now we could rewrite these if we wanted to. We could write this as Q sub A minus Q sub B minus Q sub C is equal to 0, where plus is in and minus is out. Or we could flip those. We could do Q sub B plus Q sub C minus Q sub A equals 0, right? Depending on how we want to do our coordinate system. So that really doesn't matter. So conservation of mass, or the continuity equation, is fairly straightforward. Now the question becomes, what about energy? What about conservation of energy? What can we say at node 1 and node 2 versus conservation of energy? All right. I want you to think of two principles, if you will. Think of a hydraulic grade line, and the hydraulic grade line is representative of an elevation, piezometric head and pressure head. So let's correlate the hydraulic grade line to a elevation going around the city block. You're standing on one corner of the city, of this city block, and this city block happens to be in a really hill area, but it's going to be a square or rectangle. And I have the choice. I want to go to the kitty corner or the catty corner, depending on what part of the United States you're from. If you're not familiar with that term, I want to go to the corner that is diagonally across from where I am. And I have the choice of either going right or left, right? So I can go left, take this sidewalk up around that block, or I can go right, take this sidewalk around the block. But whenever I get to the end over there, those two converge. And what is the elevation difference between where I started and where I ended? And how is it different depending upon which path I took? So how is the elevation difference between where I started? Okay, so let me just draw a simple picture here. So this is on the back of notes, but so don't mind that, it's up there. So I'm going to start over here. Okay, and I have a choice of going down that path or going down this path. And I want to end up over here. That's a loop. And the question is, how is delta Z? So we said contour lines. We're going to correlate this to contour lines. So let's see, A, B, C, D. So the change in elevation along AB equals, or how does that compare? I want to know how that compares versus the delta elevation of CD. How do those two compare? They got to be equal, yeah. We end up in the exact same place, so, and we may go up and down, but the bottom line is when we end up the same place where we start at the same place, we end up the same place, the change in elevation has to be the same. Can't be any otherwise, right? Okay. Energy grade lines and hydraulic grade lines are in essence scalars. They represent a magnitude. They don't represent a given direction, they represent a magnitude. So the hydraulic grade line at a given point is that it's a hydraulic head, it's a length, meters or feet. So correlating that to our problem over here is the same thing. If I say that the head loss, which is also a length, so let me take a step back before I go to head loss. If I was to draw the hydraulic grade line from 1 to 2, and I drew it along B, and then I drew it along C, the start point would be the same, and the end point would be the same, right? Now, there may be other stuff going inside, but the bottom line is I start at the same point and I end at the same point, all right? Now, the hydraulic grade line, the difference in a hydraulic grade line represents the head loss. So, what can I say about the head loss across B versus the head loss across C? They have to be equal. That's the whole concept of what we're trying to learn today. Well, not the entire everything, but that's the big thing right there. They have to be equal.
What's the principle behind that? Are they equal?
Okay, so are we comfortable with saying that the hydraulic grade line represents a length or an elevation? So correlate that back to the block problem, going around a block. I have some Z right here, Z sub 1. And over here I have Z sub 2. And it doesn't matter how I go from 1 to 2, whether I take A to B or C to D, the elevation difference between those two is exactly the same. Okay, comfortable with that, Mark? Okay. So, yeah, so if we take the concept of an elevation back to our hydraulic grade line represents an elevation, which it does. Okay, so when we go from node 1 to node 2, it's the same concept, and if the hydraulic grade line from 1 to 2 ends up in the same place for pipes B and C, then the head loss has to be the same. Because the head loss is nothing more than the change in the hydraulic grade line. If I have, and we could use the energy grade line too, but the hydraulic grade line has some advantages. I don't want to go into the nitty-gritty details right now, but assume if I did really quickly a reservoir going over to another reservoir, and I'm not going to worry about minor losses right now. They work into the equation just fine. We could do that just fine. But simply put, I could draw the hydraulic grade line right there. And I could have another hydraulic grade line of another branch that maybe did something like this. And I didn't draw that very well. It couldn't come down that far, but maybe it'd come down there. You know, or there was some more minor losses in there or something. But you get my point. But yes, there may be something different going on each side of those pipelines. But the bottom line is that I start at the same point and I end at the same point. Therefore, the head loss across the two must be the same. Aaron.
So it doesn't matter whether you've got different size pipes,
Correct.
even valves or anything in there?
Yeah, so let's do a little example.
If that, I understand that they're the same size, but it can.
Throw a few valves in here. So here's B and here's C. A, B, C, and D. Now A and B are easy. They're single conduits. We've already done those. We've solved that problem. Okay. And now I have B that is twice as long. So the length of B is equal to 2 times the length of C. The diameter of B is equal to 1/2 of C. Whoops, diameter C. So it's half the size. C is a 12-inch pipe. B is a 6-inch pipe. B is twice as long. B has 2 valves on it. C has no valves on it. And yet, if I wanted to compare the head loss across B versus the head loss across C, I have to say 1. That they are equal, right? Has to be equal. Okay, well, how is that physically possible? Okay, what's changing in our system that makes this allowable, that physically makes this allowable? We've got 2 equations so far. We've got continuity equation and we've got the energy equation. We're going to write the energy equation around pipe B. We're going to write the energy equation around pipe C. We know the head loss of those two has to be equal. So what's different? What's going to be different about B versus C?
You have a lot more minor losses.
it is going to have minor losses. And so if it has more minor losses and it still has friction losses, what changes to make this work? You're kind of on the right track, the pressure, but pressure can correlate to the hydraulic grade line. So it's, yeah, pressure is going to be, it's not going to be different because we're going to start with the same pressure. If we correlate hydraulic grade line to pressure, start with the same pressure and end with the same pressure. So we're getting there though, thinking about it. What else can change? The velocity. Okay, and if the velocity changes and the pipes are different diameters, what else changes? The flow rate. So velocity and flow rate are the things that change. Just because a pipe splits at a junction does not mean that half the flow goes one way and half goes the other way. Right? There's the key right there. The flow rates are not equivalent. In fact, they're not even, the flow rate in B in the second problem here would not even be half the flow rate in C. It'd probably be like a quarter of the flow rate or even less. So the velocity adjusts, which means the flow rates adjust, or you can look at that either way. The flow rate adjusts or the velocity adjusts, or the velocity adjusts or the flow rate adjusts, to account for the fact that the head loss is different. If I have a really long pipe with a smaller diameter, I'm going to get much, much less flow through it than the other pipe, but the two are going to be balanced. Because if they weren't balanced, what would happen? Well, if flow is going across B, and if they weren't balanced, flow would come across C, and then it would come back up towards B, but where would it go? We haven't talked about pulling water out of that yet. We're just saying they split. And it can't go back up B because B is sending flow down. That wouldn't be physically possible. So the flow rates adjust to accommodate that. All right. And I don't know why, I think it's human nature for us when we see, I was the same way when I was a student, when you see it split, you think, oh, we're just half flow goes this way, half goes that. No, not true. Right? Not true. Now, if they're exactly the same size, the same length, the same roughness, the same everything, well, yes, then they would split. They'd have to split, and you'd get half the flow in one, half the other. But if there's one little thing different about them, it's going to balance itself out. The equations have to balance themselves out. The system has to balance itself out. All right? Because if one of them produced a higher head down at the other end, it would flow backwards. So the physics, the natural part of the system just works. So that's the concept for today. Laura.
So you don't try and control either way at all?
Well, that's a really interesting question. I love these questions because let's assume that we only needed so much flow in one of the pipelines versus the other one. Now realize we haven't talked about pulling flow out of the pipelines yet. When you change the flow rate, then you're going to change how the system behaves, but the heads at the respective junctions still have to be equal. Okay? So if I wanted less flow in B, for example, I would then throw in another valve, which would then change the minor losses. It would increase the minor losses, which would slow the flow down through B. And I'm not sure that C would necessarily pick up more flow because it may pick up a little bit. We may reduce the flow overall in our whole system. But yeah, we could control the flow by adding more losses, sticking a valve. Okay. Now, if I happen to come along here and say, okay, I'm going to pull, and we'll eventually, this is where we're headed. And what happens if I put another pipe that came off here that went to a house and people used the water? Well, if they were using so much water that B couldn't supply that, then C would actually send water back that direction. But
So, Doctor, they always balance out the way you're saying? They always balance out?
yes, they always balance out in the sense that the head loss at the junctions does not change. Well, that's an incorrect. Can't say it doesn't change, because it does change. But the hydraulic grade line at node 1 and the hydraulic grade line at node 2, the difference across those two is the same for branch pipes.
You're saying?
The same. The head loss across each branch is the same. Did I say that the hydraulic grade line is the same? I didn't mean that. I meant to say that the change in the hydraulic grade line from 1 to 2 is always the same. Even if the flow ends up going back up, pipeline B, like we actually start pulling flow out, well, we still, if we counted across B, we would go down until we take the flow out, and we'd account for that. But now the flow would be coming from the other direction, so which direction would we going to be going up the hydraulic grade line? We'd be going up the hydraulic grade line. It's like walking down a hill and come back up the other side. And when we got to node 2, the delta is going to be the same as for pipe C. Has to be. No exceptions. No funny little rules.
This is also in real life.
Say that again, sorry.
This thing that we're studying, does that happen in real life?
Yes. Yes, this isn't an academic exercise. This is real life. This is how it behaves. This is how you design by understanding that principle right there. Okay.
So would you ever put any sort of valve at the junctions to make it kind of go one, like, can you control it more?
One-way valve.
Okay. Okay. Let me separate these two questions. So the question was, do you ever put a valve at one of the junctions to control it more? And the other question was, like a one-way valve. Well, the first question is yes. Yes, you can put a valve down here, and it really doesn't matter if the valve's down here, up in there, it's going to do the same thing. It's going to create head loss to control the flow. We think we're shutting the flow down, but in reality, all a valve does is create more head loss until you get to the point where such a small opening, the velocities are so high, it's extremely high amount of head loss, or you close it all the way and now the flow shut off. And if the flow shut off, then that changes the game completely, because now they're no longer branch pipes. And this is the same, it's true for a one-way valve. Aaron talks about a one-way valve. If you stuck a one-way valve on there, the one-way valve would represent a loss. If you're going across it, the flow is moving across it, it has loss, but it doesn't allow any flow to go the other direction. Well, if you don't allow any flow to go the other direction, now you're in an entirely different scenario, because it becomes a single pipe going out to nowhere and stopping. That's not a branch pipe. It's not a branch system. Okay. All right. You doing okay with that? Okay. All right. Well, that's 2. What about 3? That pen's not very good, is it? Did not intend that to be a dashed line. Well, there's really nothing different about this, is there? Q sub A is going to equal Q sub B plus Q sub C plus Q sub D. And the opposite thing. B plus C plus D is going to equal Q sub E. And again, assuming that we are not pulling any flow out of the system. And that the head loss across B is going to be equal to the head loss across C, which is going to be equal to the head loss across D. This is like our walking around the block concept, but now we're going to cut through the block. But we still end up 0.1 to 0.2, we still have the same delta Z across those two. So it doesn't matter how many branches we have, how much head loss each branch has. If it has flow going through it, the system is going to balance, And the head loss across those individual branches are going to be the same. Okay. And it's going to compensate by adjusting the flow rate. Now, that's not to say, and maybe some of you are getting a little caught up here, that's not to say that the whole thing doesn't act like a system. In other words, if I had 3 pipes and the flow was going through them, and I decided I wanted to change those 3 pipes into larger pipes, my flow rate would not stay the same. My flow rate across the whole system would not stay the same. Q sub A would increase. Q sub E would increase because I've changed now the flow capacity across my 3 pipes. So the head loss across the system can change if we change something in the system, but the concept of it being the same for all 3 has to be true. Right? But if I put valves on all 3 of these down here and crank down those valves, yes, then my flow rate through A and my flow rate through E would drop drastically. Have to. Okay. Not the head loss itself will not stay the same, but the head loss across all 3 of those pipes are going to be equal. So that's the point here. This right here, if I change something in the system, the head loss does not stay the same, but they do stay equivalent. If I change the flow rate somehow, if I add more pressure in pipe A, then I'm going to get more flow, and I'm also going to get more head loss. But the head loss across all 3 is still going to be the same. It's all going to be equal to each other. You have to be careful with my wording. Yes, they're all 3 going to be equal, but all 3 of them are going to change. All 3 of them could double, they could be cut in half, but they're still going to be equivalent to each other, although they can change. All right? So now we can take the concepts that we learned for single pipes, find the head loss, find the flow rate, find the size of the diameter, and apply to this concept. Let me say that again. We can take the principles that we already understand for single pipelines, calculate the head loss, calculate the flow rate, size the diameter, and apply it to this scenario, because even though we have more pipes, we also now have more equations. We have an energy equation across each one of the pipes, and we have a continuity equation at every node. Okay. Aaron.
So what happens if you put a branch in the middle of B? Does that change it? Or would it just add another equation because you have 2 pipes coming out of B and they both end at E?
So you're saying that if I did this?
No, and those pipes go all the way to the node 2 with B split.
Oh, okay.
You would just add a 4th equation, you have 4 lines between A and B, or between 1 and 2.
So let's say I had one that came over here, and this one came through there. Okay. A little more complex, because let's call this B prime and this B double prime. Okay. Now, is the head loss across B prime and B double prime equal to the head loss across B? No, because it didn't start in the same location. Okay. Could we solve this using the same principles as down here? Yeah, we could, because we'd have to calculate now. It'd be an ugly system to solve. We'd have to calculate what is the head loss up to this node here. Call this node 3. Okay. And then we would take node 3 and we would split that back up there to figure out what's going on through B prime and B double prime. And it's the same principle, but much more want to say complicated, but the arithmetic just, the accounting side, keeping track of everything gets really ugly in that case, okay? We can do it. In fact, in essence, we will do that when we hit pipe networks. Because pipe networks are nothing more than branch systems. We put a system in a city, and the pipe goes around the block, and it joins back up with the regular system. Now, we get a little, there's a little more complexity to that, because now we start pulling out flow for houses to use and businesses to use and industry to use. But this represents nothing more than the flow going over and then going around a couple other blocks and then coming back to the main city block. So we're headed there. Okay.
So B prime and B double prime would equal to each other this time?
Yes. Yeah, good point. Yeah. Head loss across B prime and B double prime would be equal to each other. The flow rate is wildly different. The head loss has to be the same, because it's starting in the same spot and in the same spot. Okay. Now, go ahead, Aaron.
So what would happen, the way you were originally drawing it, where you have the two nodes in the middle? And then B continues on to node 2.
Same concept, that if I had this down here,
Yeah.
D prime and D double prime, that the head loss from that node to that node is both across both of those is going to be equivalent. And not only are they going to be equivalent, but the one in the middle is going to be equivalent to them as well.
So with, from node 1 to node 2, are you the same across D as it would C,
Yes.
the entire system?
Yep. Yep. Does not matter. It would have to be the same. We just got some interior stuff going on there. We don't know how the flow splits. So we might, we'd have to solve the bigger system
And then break down.
and have the smaller system, and we might have to then go backwards and solve the small system to feed back into the big system to get the right answer.
It would just be more complex.
Yeah. Yeah, it's just it's a bigger accounting problem. We got the same thing. We got the same thing going on. It's not any different equations. It's just we got more of the equations, and you have to keep track of them. And that's where the complexity comes in. Is it just gets keep track of now these 20 equations rather than the 6 that we had before. Okay. Now, to make our life a little easier, I want to add something here. One of these pens seems to be working very well today. If I look at the head loss, the total head loss is equal to, for a single pipe, F L over D. I'm going to write this in terms of Q. Q squared divided by 2G A squared plus the sum of all the individual case of i's times Q squared divided by 2G A squared. And this, once again, is for a single pipe. Okay. Now, often what we want to find in these type of scenarios with branch systems is the flow rate. We can find the head loss. We can size the diameter. But those really boil down to a bunch of single problems. Break the system into its parts and solve each part separately. But if I want to find out what's going on in the whole system, I'm looking for flow rates. Now, well, let me take a step back. As we move into this and we start doing pipe networks, we find that we can either solve for the head, the hydraulic grade line everywhere, or we can solve for the flow rate everywhere. And then once we get one of those other ones, then we can come back and do the other one. So we'll get to the point where we'll call these either the flow equations or the head equations. We're not going to do the head equations in this class, because I've found that students relate better to the flow equations. And if once we find the flow rate, then we can go back and calculate the head. So rather than trying to muddy the water, we're going to stay with flow rates. Physically, I think it makes more sense. So if I want to stay with the flow rate becomes the unknown. All right, so Q is unknown. In that case, if you look at this, I can take everything that's outlined in the red, and I can let that equal some constant. Doesn't look red up there, does it? Okay, everything that's circled up there. So if I do that, then my equation simply becomes the head loss is equal to C Q squared. Now, could I update C? Yes, I could. Let's say, for example, I didn't know the friction factor. And so I solved for the flow rate. Then I said, oh, I'm going to go in and correct my friction factor now. Then I update C. Then I go back and solve for my flow rate again. It's just that iterative process, right? So it's not that hard to imagine C if needed. But to make life easier, as we start getting into this big, complex branch network that has these different variables, I mean, different equations, and they just get kind of, but it's the same thing. It's just the same thing over and over again. I simplify it. So if this was pipe 1, I'd be C sub 1 times Q sub 1 squared, right? Everyone grasp that concept? We're not introducing a new equation here. We're introducing new notation. And the notation makes our life easier. Okay. Okay, so I'm going to run out of time here. If I was to work an example, okay, so given pipe network, a pipe branch, and we'll keep life simple. Same thing, A branches around to D, and in the middle here we have B and C, okay? And I know that the pressure at node 1, so P at 1 is equal to 80 PSI. And I know at node 2, the pressure is equal to 50 PSI. It's kind of a big drop, but that's okay. So we have a drop across those two. So my head loss then, or my delta P, is going to be 30 PSI. And I could calculate then the head loss across there, right? Head loss would be P sub 1 over gamma plus Z sub 1 minus P sub 2 over gamma plus Z sub 2. Now, if we assume that there is no elevation change, so Z sub 1 equals 0 and Z sub 2 equals 0, then all I have to do is calculate my pressure head at one, my pressure head at the other, and I know the head loss. Okay. Now B, of course, this pipe over here is going to have F sub B, L sub B, D sub B, and down here at C, I'm going to have F sub C, L sub B, L sub C, sorry, L sub C, and D sub C. And let's say that we know the friction factors, or we take a good guess, okay? But we don't know, we want to find the flow rate. The concept is to find Q sub B and Q sub C. So note, yes. You can't see what, which one? Right here? F sub C, L. Up here? That's F sub B right here. F sub B times L.
one, yeah, I can't see what's on the subscript of that, what is this?
Yeah, there's no, this is and. Find Q sub B and Q sub C,
Oh, okay, that's
the
fine.
flow rate. Is that,
I couldn't see what it is.
okay, sorry.
Okay.
Trying to hurry and my handwriting gets sloppy when I try to hurry. So in this particular case here, we're not caring about the flow rate in A and the flow rate in D. I mean, we could solve those once we know the flow rate across our pipe network here, right? Those are single pipes. What I do know that the hydraulic grade line, or the head loss in B has to equal the head loss in C. And I also know that this head loss across each one has to equal that right there, right? So this one actually falls right out, because if I know the head loss across my whole system, I now can take that and plug that into each one of those equations and find the flow rate. So for example, the head loss across B would be equal to the head loss across my whole system up there, which would equal F sub B times L sub B times D sub B times then Q sub B squared divided by 2G A sub B squared, or in simple notation, C sub B times Q sub B squared. Simple notation is a lot easier, right? Zach, how we doing? Okay. So now if we know the head loss, the flow rate falls right out. And I plug these known values in. Once again, if the friction factor isn't known, go ahead and solve for it. Go to Reynolds or the Moody diagram, calculate the Reynolds number, Moody diagram, get the new friction factor, update C, solve it again, right? It's the same thing over and over again. If I don't know the head loss, but the flow rate in A is known, so if Q sub A is known, well, if I know Q sub A, I automatically know Q sub D, because what comes in goes around my loops and goes out D has to be equivalent, right? It comes in here, goes around, and the flow in D is known too. But I don't know the flow split across those two, okay? So Q sub A is known, but the head loss and split of Q sub B and Q sub C is unknown. Use more of my screen there, sorry. So my additional equation for this one is where I let the head loss of B equal the head loss of C, and I set those two equal. And then I also know that Q sub A has to equal Q sub B plus Q sub C. And those three equations right there allow me to solve for Q sub B and Q sub C. And then I can take either one of those two and plug it into its head loss equation to get the total head loss across that system. It doesn't matter which one I use because they're the same. Okay. Any final questions? We're about out of time here, but any final questions? Those online have been kind of quiet today. Any questions from those online? Okay. Well, with that, let's call that a day then. I will post the homework and we'll see you on Wednesday.
Dr. Savage, what did we decide on our meeting? What time? 'Cause there was so much back.
Yeah,
What
I
time?
think it's tomorrow at 10 or something.
Because I wasn't sure. It was like, you said something and then Karen something else and then didn't know.
Yeah, so when I get